Hi guys, I will be discussing UVA problem number 12128, escape from enemy territory. Uh, so, I will not read the problem statement, I will just explain the question. The question says that you have a grid and uh, it says that you are a group of soldiers and the entire map is in the form of a grid. You have a starting position and you have an ending position. You have to reach the ending position from the starting position, and there are some enemy outpost, or you can say basically these are cells from which you want to stay as far away as possible. So the problem statement asks us to find a route. We need to output the length uh, of the route such that whenever we are at a point, we measure the distances. Suppose we are at suppose this is a route, right? So in this route, the distances from the enemy outposts will be calculated at each of these nodes, at each of these cells, and for this cell, we will calculate which enemy outpost is closest to it, the distance. For example, here the distance is 2. The distance is in the form of a Manhattan distance. And in this path, then for all these cells, we will find what is the minimum value of uh, distances calculated at each cell. For example, here the value will be 2 because this outpost is the closest. Um, for this cell, it will be 3. For this, it will be 1. For this, it will be 2, and so on. So for this, the answer will be 1. So basically, in this path, we have to find the minimum or the closest distance from any enemy outpost at any cell. Like out of all the cells, we will pick the one which is the smallest. And we want to choose a path which maximizes this smallest value. And if there are multiple paths, then we have to output the one which has the minimum distance. So this is the problem statement, and it is given that the size of the grid, the number of rows and number of columns are within the range of 10,000, and the total number of enemy outposts is 10 to the power 4. Also, it is not necessary to avoid all the enemy outposts. For example, suppose if in this case itself, if there were enemy outposts at all these points, then there was no way to avoid it. Whatever path we took, the answer for that path would be 0 because the minimum distance would be 0. We will be crossing an enemy outpost no matter whatever path we take, but that is a valid result. We will print 0 in that case. So now on how to solve this problem. Well, I'd like to divide this into some sub problems first, and we will try to find out the solution to those sub problems. You can even try doing them on your own. So the first sub problem is, and see, whenever we are calculating a path, like in a path, we are calculating, what is the minimum distance from any enemy outpost at any cell, like whichever cell gives the minimum. We first need to find for all cells, uh, what is the minimum distance from all the enemy outposts. For example, suppose we are talking about, let's say, this cell. We might be analyzing some path and we are using this cell for that path. In that case, we just have these two cells, right? These two enemy outposts. So for this, the answer will be 3, and with respect to this one, it will be 3, and with respect to that one, it will be 1, 2, 3, 4, 5. It would be 5. The distances are Manhattan distances. So we would have this as 3. And this will be constant. See, in an analysis, once we have calculated this distance, because these enemy outposts are fixed, right? So the first thing that we would want to do is find these values for all the cells, and you can try solving this on your own. This is one of the subproblems. Now, for the solution to this subproblem, what would we do? So this can be done with a simple BFS search, and see, the intuition for that is Manhattan distances takes the sum of the vertical height and the horizontal height, right? That means um, if we have to calculate Manhattan distance between this point and this point, it would be 2 because we're moving vertical up and right one step. Now, how would a BFS help us in calculating these values? Think of it like this. We want to calculate the minimum um, distance from every enemy outpost. So if I suppose start a BFS and initially I place these two enemy outposts in my BFS queue. That is, in my queue I place the index 2 comma 1 and 2 comma 3, and we would do normally, we would pop this element, and for all its adjacent elements, if they have not been visited, we would increment their distances as 1 and mark them as visited, and then push them again in the queue. Now the thing is, this element, this for example, if you want to calculate for this cell, whichever outpost will reach it first will have the minimum distance. For example, because what an outpost, what we do in a BFS is we either move one step up, one step right, down, or bottom when we pick an element. So if suppose we want to check for the cell to our right and that cell has already been visited, that means there must have been some other outpost closer to this cell because of which it has been visited already. So a cell will be marked by the outpost which it is closest to if we do a simple BFS. Another way to think about is if I wanted to calculate the shortest distances in this graph. The edges in this graph can be thought of like this. These could be thought of as the edges of unit length. So for that, we can use the BFS algorithm if all the edges in a graph are of the same length. So that, and uh, node, whichever node for particular cell, whichever outpost has the smallest distance to it, um, that will mark it first, and for that we will store the minimum distance from uh, with respect to all the outposts. So I think it should be clear why we can do a BFS. I think the distance one is a bit more clear because whichever outpost is closer, uh, we would reach this cell first because of this outpost, because it is closer, and BFS is usually used to find the shortest distances if all the edges of the same type or of unit length in this case. So what we can do is we can simply start a BFS from uh, initially by putting all the outposts in the queue. For example, if here also an outpost was here, and then we will pop in any outpost. For example, if we initially pop this one from the queue, then we will mark this as 0. I will make another I guess matrix for this. For example, we will first push in the queue, like I said, 2 comma 1 and 2 comma 3, having a distance of 0 initially, because these cells are enemy outposts themselves, so their minimum distance is 0. So we will pop them out. We'll pop them out suppose we pop this one out, we will mark it as 0. We will visit all of its neighbors, and if those neighbors have not been visited, that means we are visiting them for the first time, that we must it must be the shortest distance. So we will increment, matlab, their distance would be the distance of the node which is popped out plus 1. So in this case, all of these would be at distance 1. And we will again push them in the queue. So now the queue will again have some more elements like 2 comma 0 with a distance of 1, and 1 comma 1 with a distance of 1, and so on. Then we will pop out this. You will see, okay, this one has already been visited, so that's fine. We don't need to worry about this. And we will mark the distances for these as 1 1 1 1. Then again we will pop any one of these red ones out and mark these distances as this one is. Suppose we pop this one out first. Mark this as 2, mark this as 2, mark this as 2. All these would be 2, and so on. So a BFS can be used to find uh, this constraint of the minimum distance from any outpost for each cell. For example, this would have a value of 2 because it's closest to this. It would have a value 3. It would have a value, I think, 4, 3, 2, and then again 3 and 4, and so on. Now, okay, this part is complete. So we have, I'll just fill this matrix completely. This would be 2, this would be 3, this would be 2, this would be 3, this would be 2, 3, and 2. And these 2 will be 1. Like, this will be 3, and this will be 3 as well. Now, what we have to do is we have to find a path which starts from A, ends at B. There can be many paths. For example, um, this is one path. But for this path, 1 is the smallest value amongst all the nodes which are a part of this path. So the answer would be 1 for this path. We can also have another path like this. In this, you see 2 is the minimum value. So answer would be 2 for this path. That is, for any cell, the minimum distance out of all the cells in this path from enemy outpost, the minimum of the minimum distances from the enemy outpost is 2. And no matter whatever path I think you take, this would be the smallest answer. 2 would be the smallest answer in this case. And actually, this is the only path in this case where the answer is 2. Like, there are multiple paths, but like there could be a path like this as well. Can draw. This is also another path. You can do something like this. But then this one is the shortest. It has a length of 14 and the minimum value is 2. So this is what we will print in it. Now, how do we find this out? And I think you can try this. If you have solved this subpart, now you have to solve A. Okay, first just solve the fact that how do we find what is like this value. Forget about the length, that is easy, but which path should we take such that we get this minimum thing as the maximum possible. So in this case, it's 2. So I'll just go on to the solution directly. What came to my mind is, and this is, I think you should remember this approach, is that if for me, like, I tried to find greedily what answer could exist, but I could not find any way to solve it greedily. So could I have some upper bounds on my answer? And this answer, this will then generalize to binary search. So the question is, if I have a path, suppose any path, and if I know that there exists path such that the answer is at least k, if I know for a fact that there exists a path such that the answer is k in it, there is a path, there is a path for which the answer is k, then I don't need to, I will not take any path for which the answer is less than k, because already have this answer with me. This is the current maximum for me. So I will try to find an answer bigger than k. And we will sort of do this using binary search. So suppose we have a way of finding out if we have an answer of, if we have a path of having an answer k for that path. So what do we know? That we know that there exists a path if we have a way of finding this out. If we have a way of finding out that there exists a path or not, such that the answer is at least k. For example, I can say that the answer is at least 1. I mean, it's so if I know that the answer is at least 1, I should try to find an answer which is greater than 1, right? Because I already have 1 or k as my established baseline right now. So this is what we'll do. We will run a binary search, and we will have a start index at 1 and end at, see, the maximum path length here I think can be 2000 something, because that is the maximum uh, Manhattan distance. I think 1999 is the maximum Manhattan distance. Uh, so of course the answer cannot be more than 2000. We are finding out this value, not worrying about the length. That is easy. Once you get to know how to find this answer. What we'll do is we will go to the mid and we will do something which we'll talk about. This will tell us that if there exists a path such that the answer is at least k. If this is true, suppose this is true, then we search in this range recursively. If this is false, then we search in this range. And then we shrink our answer and find the exact answer. For example, if I say that, suppose um, I'm searching in the range 1 to 5, not 1 to 2000 right now, and I search for 3, and I do something and I find out that okay, yes, the answer can at least be 3. Then I'll search in this range. And I also have an answer variable. So when I get this confirmation that the answer would at least be 3, I'll make this answer as 3 for now. Then I'll search in this range. I'll have my mid at 4. If it gives me that, hey, the answer can not be at least 4, that means the answer cannot be 4 and it cannot be more than 4. So then I'll search in this range. This is the range from 3 to 3. And I know the answer for this exists. So it's a simple binary search now. But how do we do this? How do we find if the answer exists at least for k? So the idea here is that if the answer exists for k, or if the answer is k or more than k, if we are saying the answer is at least k, then the answer can either be k or can either be more than k. It can be k plus 1, k plus 2, and k plus n. But when we are taking a path, can the path have a cell such that its value is less than k? Suppose I have k as 4, and I am taking some path, and there is a cell of uh, having value 2 in that path. Then the answer cannot be 4. See, the answer will 2 is smaller than 4, right? So the answer will either be 2 or something smaller than 2. So what I can do is, so I have to ensure that I am not taking any path less than k, any cell less than k in that path. So what you can do is you can treat any cell having length, any cell having length, not length, answer for this value which you have calculated, whatever we call it, less than k as a blocked cell. That means we cannot move along that cell. We cannot cross it. So it's now a problem of finding out whether a path exists from point A to point B, given we have some cells which we can traverse and some cells which we cannot traverse. For example, I'll just take this same grid. Yeah. So in this grid, if I'm saying that suppose if the answer is 2, if I want to find out whether the answer is at least 2 or more than 2, it can be 2 or something greater than 2. So I cannot take any path which is less than 2. So what I'll do is I will mark all these paths less than 2 as blocked paths. Even the outpost itself will be blocked. We cannot go through the outpost. This means that we cannot go through any of these cells. The value for this I think was 2. Value for this was 2. And now we can pass through all these other cells. We just have to check if a path exists. For example, here is a path which exists. Okay. But remember, if we do this a little smartly, if we do this using BFS will give us the shortest path from point A to point B. If I run a BFS from point A, and while doing the BFS, if I actually, in my queue, if I pop out point B at some point, and I also store the distance of point B, I will be able to get the minimum distance simply by using the BFS. So together we will get both validation, whether that K, we can have an answer greater than K, and we will all, if we can get an answer greater than equal to K, we will also get the shortest path if we are doing BFS. So this is the way you solve it. To summarize it, first you calculate these values. What are these values? These values are for each cell out of all the outposts, what is the distance of the closest outpost to it? Then you have that when you have got these values, you will simply binary search, because you have to find the that path which gives the maximum, that path for which out of all the cells these values, the minimum of these values is the maximum. So you can set some upper bounds for this maximum, uh, and then you can binary search over the answer. And by binary search, you can just block off all the cells. Binary search is of the nature that when you are binary searching for an element k, that means that you are checking basically if there is a path having this answer greater than equal to k, not necessarily k, greater than equal to k. Um, and to check that, all the cells having values less than k will be blocked, and you simply have to check if there exists a path. So that is all for this problem. Thank you very much. Bye.